What's up guys, this is the Round Bottom Flask and welcome to the part 2 of our video lecture series for Colligative Property Subsolutions. In this video, I will be discussing how non-volatile solutes raise the boiling point and lower the freezing point of your solution. So I have discussed in part 1 of the video lecture series how the interactions between solute and solvent particles lower the vapor pressure of your solution in comparison to the pure solvent. So the YouTube link of the part 1 of the video lecture series is in the description below this video. I suggest that you watch it first before you proceed watching this video. So because of that vapor pressure lowering, and as I've said in the part 1 of my video lecture series, that vapor pressure and boiling point are directly related to each other, this same effect due to the solute and solvent interactions will raise the boiling point of your solution. So I have shown here as what we call as the phase diagram. So ano ni siya ang ginatawag nga phase diagram? So phase diagram, simply put, is just a pressure temperature graph of a pure substance and a mixture, showing the different states that the pure substance or the mixture can adapt at the given pressure and temperature range. So sa graph, we have the y-axis or the x-axis rather for your temperature and the y-axis for your for the pressure of the pure substance or the mixture. So from left to right, the temperature increases, and from bottom to top, the pressure increases. So you can see here that in the phase diagram of a hypothetical substance, it exhibits three phases: the solid, the liquid, and the gas. And you can see that may ari kita lines nga separate between these phases, and these are what we call as the phase boundaries. So to elaborate, these phase boundaries are actually specific pressures and temperatures wherein ang mga phases nga gina-separate sa phase boundaries ga-exist at equilibrium with each other. So ano ning maghambal ka nga at equilibrium with each other? So let's take this phase boundary here, the boundary that separates between the liquid and the gas phase. So this liquid gas phase boundary, kung ang specific temperature and pressure mo, let's say this point here, gato pa sa phase boundary between some liquid and the gas. That means nga at that specific pressure and temperature, the liquid phase and the gas phase of the pure substance exists at the same time. I believe this is quite this is just an exaggeration, because we have already discussed sa part 1 sa video lecture nga ang liquid kag ang gas naga-exist at any temperature range, right? Kay some of the liquid, especially the the liquid molecules at the surface of the bulk liquid can escape to the gas phase, and at the same time ang gas phase ang vapor naga-condense man siya back to the liquid phase. Karon, so ano ning purpose ang phase boundaries? Kay basically sa bisan ano nga temperature, as long as the substance is a liquid at that temperature and pressure, ara Japon ang gas phase, di ba? So this means that at this phase boundary, they are already in equilibrium with each other, that the molecules or the liquid molecules at the middle of the bulk of the liquid will now escape to the gas phase. It's no longer on the surface, but ara na siya ga-occur man sa tunga sang bulk sang liquid. So this usually occurs when the substance already boils. Okay, so that means that this liquid phase boundary, this liquid gas phase boundary exhibits the boiling point of the pure substance at that specific pressure. Okay? Amo lang na siya. Now, if you notice these red lines here, this is the phase boundary for your solution. And if you notice, the liquid gas phase boundary of your solution is far more to the right in comparison with the liquid gas phase boundary of the pure solvent. So what does that mean? Since nag-move siya to the right, that means mataas man ang boiling points ng imong pure solution because increasing ang temperature from left to right. So if you can see here, nag-move ang phase boundary pa right. So matabo is ma-shift man ni pa right ang tanan nga temperature. So ang matabo is mas taas nga temperature ang kinahanglan mo for the solution to boil in comparison to the pure solvent, given they occur at the same pressure. So how, as to what degree the solute raises the boiling point of your solution. So this is explained by this equation here, wherein the delta TB is the difference between the boiling point of your solution and your pure solvent. Okay? So since C solution is mas taas boiling point compared kay solvent, so para hindi mag-negative ang delta TB mo or ang change in boiling point mo, your minuend will be the boiling point of your solution and the subtrahend will be the boiling point of your solvent. So to show here, and your Kb is what we call as the molal boiling point elevation constant, which is actually an intensive property. So it's unique for every liquid, just like your boiling point. And M is the molality of the solution. So to refresh your memory, molality is a unit of concentration, which is equal to the moles of solute per kilograms of solvent. And I is the Vanatop factor, which I will explain later on in this video. So I will show you here, before ko i-show gali ang tables of molal boiling point elevation constant. So I'll show you here how to manipulate this equation. So we know that delta TB is this one, right? So we substitute this expression to this one here, and this will give you this expression here. Okay, so to get the boiling point of your solution, transfer delta TB of your solvent to the other side of the equation. So from negative, this will become positive, and thus from this starting fundamental equation, you can derive an equation that will give you the boiling point of your solution, which is this equation here, which will be our quote-unquote working equation. So here are the molal boiling point elevation constants of some of the common solvents. So I suggest for the context of general chemistry that you memorize the molal boiling point elevation constant of water, which is 0.512 degrees centigrade per molal. So to further discuss Vanatop factor, let's have this hypothetical situation here, or let's rather observe the dissolution of a strong electrolyte such as sodium chloride at the molecular level. Now remember that in the solvation process, when sodium chloride is dissolved in water, the water molecules will form ion dipole interactions with the chloride anions and the sodium anions, right? So since they are non-electrolytes, the role of the water molecules here is they try to rip apart the sodium chloride crystal, which is shown here, and thus by ripping it apart, the water molecules will form some sort of a cage around these individual ions. So what happens here? Now, because these ions become separate, they will act as if they are a single distinct quote-unquote entity in the solution that are independent with each other. And these independent, distinct, and quote-unquote entities will have a separate effect in the colligative properties of your solution. So to make it short, these individual ions in an electrolyte solution will act as if they are an individual solute. So let's say you have 4 formula units of sodium chloride of solid sodium chloride, and when you dissolve this four formula units of sodium chloride, di ba ma-separate na sila into your sodium cations and your chloride anions. So they will act independently of each other, and thus it will appear in your solution that you will have 8 components or 8 units of your solute in the solution. And since colligative properties is all about numbers, so they will act, these 8 ions, a total of 8 ions will act on the colligative properties of your solution. They will affect these colligative properties of the solution. So where does the Vanatop factor come in? So the Vanatop factor is actually some sort of a correction factor that takes into account the number of ions produced when dissolved in your solution. So for example, since sodium chloride forms 2 ions in your solution, the sodium cation, the chloride anion, it will have a limiting or a theoretical Vanatop factor of 2.0. Okay? So potassium sulfate will, since it produces 3 ions, the 2 potassium ions as indicated by the subscript 2 here in your potassium sulfate, and 1 sulfate anion, so that is a total of 3, and thus it will the limiting value of the Vanatop factor will be equal to 3. So basically your Vanatop factor is just the number of ions produced per formula unit of your strong electrolyte solution. Now, if you notice here, the Vanatop factors of each of your electrolytes is not equal to their theoretical value, okay? However, for a non-electrolyte, such as sucrose, since wala man sila ga-dissociate into respective ions, ang ilang Vanatop factor is 1. Kaya kung mag-dissolve siya, for example, if you have 1 unit of a non-electrolyte such as sucrose, if you dissolve it in a solvent, the formula unit will still be 1. Okay? Kaya wala man siya na breakdown into 2 parts sang nag-dissolve siya sa solution, unlike sa aton nga electrolytes. Okay? Or strong electrolytes rather. So going back to our strong electrolytes, if you've observed nga wala sila galabot gid sa ideal value nila. Okay? However, if you notice here, their values are pretty close to their limiting or theoretical values. For example, sodium chloride across all concentrations, the limiting value or their Vanatop factor is close to 2. Okay, same goes with potassium and magnesium sulfate. But if you notice here that the experimental Vanatop factor decreases with increasing concentration. Now, it's not as pronounced as that if you've seen in sodium chloride, but it's very pronounced in potassium and magnesium sulfate. So let's take, for example, potassium sulfate. So see potassium sulfate at 0.001 molar, iya nga Vanatop factor is 2.84. Kung i-round off mo siya to the nearest whole value, 3, which is ang iya nga ideal or theoretical Vanatop factor. Pero you increase the concentration by 1 order of magnitude. So from 0.01, mangin 0.1 siya, you increase the concentration 10 times, the Vanatop factor drops from 2.84 to 2.70. Now, you increase the Van't-Hoff factor another 10 times, and it drops drastically from 2.73 to 2.32. So at 0.1 molar, 2.32 na ang Van't-Hoff factor ka potassium sulfate. Karon, i-round off mo siya, so the nearest whole number, hindi na siya mag-3. Mas lapit na siya sa 2 in comparison to 3. So what is the cause? The explanation nga may-ari kita sang decreasing trend sang Van't-Hoff factor with increasing molal concentration sang aton nga solution. This is because of the formation of what we call as ion pairs. So what are these ion pairs? So remember guys that let's go back sa the solution sang sodium chloride in solution. Okay, now when the salt is dissolved, it will dissociate into its respective ions, right? And the water molecules will form a cage around it due to their ion dipole interactions. But remember that water is not a neutral molecule, is not an ionic in nature, but rather it is a molecule. Although it has partial positive and partial negative parts or portions, it is not a pure charge. Okay, so for example, si chloride and ion, kung ma-attract niya ang positively charged component sang or partially positive charged portion sa water molecules, palibutan siya sa water, right? But it does not completely mask out or completely dissipate the charge of your chloride and ion. Same goes with the sodium and cation. So since these ions move randomly in the solution surrounded with water molecules which does not completely dissipate their charge, there is a possibility nga they will come in close proximity with each other. And coming in close proximity with each other, these sodium and chloride ions, they will exert electrostatic attraction with each other. And because of this electrostatic attraction, they will form these ion pairs here. And these ion pairs will act as if they are one entity instead of two separate entities. So how is this related to the decreasing trend of Van't-Hoff factor with increasing concentration? Now remember nga, since ga-increase ang concentration mo, ga-increase man ang number sang ions nga ara sa imo solution. The greater the number of ions in the solution, the greater the probability that oppositely charged ions will come in close proximity with each other, and thus they will the greater the possibility of forming ion pairs. Because since ang ion pairs, they act as one entity instead of two separate entities, so there will be some that will sodium and chloride and ions nga will act separately, that will affect the colligative properties of your solution, and there will be some sodium ions and chloride and ions that will sort of act as one, kag they will affect the colligative property as one entity, and the magnitude of those two separate entities and those one same entity, the magnitude of their effect to the colligative properties will still be equal with each other. So kung mas damo ang imo ion pairs, mas mangin jutay ang effects ng colligative property, kag mas majutay mangin ang effects ng electrolyte sa colligative property, kag mas madubo ang imo nga Van't-Hoff factor, or mas ma-deviate siya sa ideal nga Van't-Hoff factor. Okay? Before I proceed, I would just like to state that Van't-Hoff factor is also applicable to other colligative properties, even vapor pressure. Okay? So let's go to the freezing point depression. Now this, the freezing point depression, on the other hand, the same solute-solvent interactions also come in play there, but contrary to boiling point elevation, this actually lowers the freezing point of your solution. If you notice here sa phase diagram, may shift kita sang aton nga solid-liquid phase boundary to the left. That means it will take a lower temperature for the liquid to cross this solid liquid phase boundary and go to the solid phase. So you will need a lower temperature for the solution to freeze. Okay. Now the magnitude of the effects of your non-volatile solute in the freezing point of your solvent is the same as, or rather the formula is the same as that for boiling point elevation. Okay, but now the delta TF here is the freezing point of the solvent minus that of the solution, because we expect, or it is observed, that the solvent will have a higher freezing point in compared to the solution. So the same units apply. So we still have the freezing point, we still have the molality of your solution and the Vanatop factor. However, KB here in the boiling point elevation equation is replaced with your KF, which is the molal freezing point depression constant, which is again another intensive property of your solvent or any substance in particular or in general. So just like what we did in the working formula or the fundamental equation for the boiling point elevation, we substitute this expression here to our delta TF in this first equation here. So you get this expression, and if we would like to know the freezing point of your solution, you have to manipulate the equation such that only freezing point of your solution is left on one side of the equation. So what I did here is that this expression and this expression here will switch places with each other. Okay, so when you transfer TF of your solution to the right side, from negative mangin positive ni siya. Same goes with this expression here, from positive mangin negative siya, and thus the final equation for the freezing point of your solution is equals to TF of your solvent minus KFMI. So here is the freezing point, a molal freezing point depression constant of some common organic solvents, common solvents, and I suggest you memorize the KF of your water, which is 1.86 degrees centigrade per mole. So how does the non-volatile solute lowers the freezing point depression? So let's try to view it at a molecular level. Okay, now remember that at the freezing point, so usually kung sa freezing point, ara na siyang ang temperature mo, ara na siya sa solid liquid nga phase boundary sang aton nga phase diagram. So that means that the freezing and melting of the liquid coexist with each other, and they occur at the same speed or the same rate. So that means nga some of the liquid molecules ga aggregate together para mag-form sang solid, kag ang iban nga solid or iban nga molecules nga ara sa solid break away para mag-form liquid. So go-occur na sila at the same rate. Now, if you add a non-volatile solute in the liquid portion of this solid liquid equilibrium phase here, what will happen, since they will exert intermolecular forces with each other, ang solute kag solvent particles, these intermolecular forces are actually much stronger in compared to between solvent molecules. Since may ari ka di solute molecules and once mag-freeze ang imong nga solvent, hindi magupod si solute molecules. Okay? So, ang matabo, since mas stronger ang attraction sa solvent kay solute, it would rather stay sa liquid phase. Thus, it will be harder for the solvent to break away from the liquid phase where it forms stronger non-covalent interactions with the solute to form your solid phase. I hope you understand what I'm saying here, okay? So let's have an example here. You add 1 kilogram of ethylene glycol antifreeze to 4,450 grams of water in your car's radiator. What are the boiling and freezing points of the solution? So I've said this in the part 1 of this video lecture series nga every time you answer a problem-solving question, you should state first the given. This helps you determine which of the following values will be needed for you to solve the question and to arrive to the correct answer. Because sa iban nga mga problem-solving questions, there are some values that are really not necessary for you to solve the question. It's just placed there to test the students' critical thinking and reading comprehension skills. Okay, so we have 1.00 kilogram of your ethylene glycol with the chemical formula of this one here. I'll just write the chemical formula para at least not only nga mas comprehensive siya isulat, but this will the chemical formula will also help you in solving for the molar mass of your ethylene glycol. So it was added to 4,450 grams of your water. Okay? There are some values that are needed to solve this pero wala siya ginbutang. So, ang isulat na lang natin siya. So, we know, since ginapangita ang boiling point and freezing point sang solution, kinahanglan man natin ang boiling point sang pure nga water. Which is, we know, which is 100 degrees centigrade. Kag ang freezing point sang pure nga water is 0 sorry about that guys, 0 degrees centigrade. Okay, we also put the molal boiling point and freezing boiling point elevation and freezing point depression constants of water. So as I've said earlier, you have to be familiar with this because you will be using this a lot in general chemistry. So the molal boiling point elevation of water is 0.512 degrees centigrade per molal, while the molal freezing point depression of your water is equals to 1.86 degrees centigrade per molal. So we write what is required. So we want the boiling point and the freezing point of your solution. So how do we solve this? So I suggest you write your working equation first. So your working equation, we have already seen that. So for boiling point is equals to the boiling point of your solution, or the boiling point of the pure water rather, plus KBMI, and for the freezing point of your solution, that is equals to the freezing point of your pure water minus KFMI. Okay? So, para kapos tandaan, ang sa boiling point plus ang sa freezing point sa solution minus. Okay? so that you will it would be it would be easier for you not to confuse between the two. Okay, so we already have the Vanatop factor. Since ethylene glycol is a non-electrolyte, so the Vanatop factor is equals to 1. Okay, we already have the boiling point and the molar boiling point elevation constant of your water and its freezing point and molar freezing point depression constant. Okay, so ang isolve na lang natin is your molality. So the molality of your water is again mole of your so the molality of your solution is the mole of your solute, which is your ethylene glycol, and the mass of your water in kilograms. Okay, so how do we solve for this? So how do we solve the number of moles? So we use the mass of ethylene glycol, then we convert it to number of moles using its molar mass. So this will be in the numerator portion. So in the numerator portion, so we have 1 kilogram of your ethylene glycol. So, and since, I'll just write it here. And since 1 kilogram is equal to 1,000 grams, that means you will have 1,000 grams of your ethylene glycol. Okay, so you convert that to mole using its molar mass. So I'll just write it here. So the molar mass of your ethylene glycol, I've already calculated this beforehand. So 62.068 grams per mole. So grams ethylene glycol which is equal to 1 mole of your ethylene glycol. So again, ang atong nga molar mass will serve as some sort of your conversion factor. Kag para ma-cancel out si grams, si numerate si 62.068 grams ara sa dalom sa denominator, kag si 1 mole ethylene glycol ara sa numerator. So this will cancel out. And since we're given the mass of water in kilograms, we have to convert this to kilograms. So we have in the denominator 4,450 grams of your water. You convert this to kilograms using their conversion factor. Nga 1 gram, 1,000 grams is equals to 1 kilogram. So si 1,000 grams, diri sa denominator sa atong conversion factor, and si kilogram diri sa numerator. Okay, so cancel out, and that is equal to 3 point rather 3.62053 molal. Okay, so we already have this one here. We substitute it to our working equation here to get the freezing point and the boiling point. So the boiling point is equals to 100 degrees centigrade plus Kb, which is 0.512 degrees centigrade per molal, multiplied by the molality, which is 3.62053. So I will not place the Vanatop factor in a 1, since any value multiplied by 1 is the value itself, right? So this will cancel out, and what you'll get is the molal boiling point, which is rounded off to 1 decimal place, is equals to 101.9 degrees centigrade. Okay, now for the freezing point, Now for the freezing point, we'll also use this formula. Substitute na lang ta diretso. So this is equal to 0 minus 1.86 degrees centigrade per molal multiplied by 3.62053 molal, which is equal to, rounded off to one decimal place, negative 6.73 degrees centigrade. So let's have another example here. What is the freezing point of an aqueous solution that boils at 106.5 degrees centigrade? So this is quite a tricky one because apart from the constants, what we just know is the boiling point of the solution. So let's write first the given. So ang boiling point ng solution obviously is equals to 106.5 degrees centigrade. Now, it was not explicitly stated what is the solvent of your solution. However, it states that it is an aqueous solution. So we know that aqueous solutions are solutions wherein the solvent is water. So now we know that the solvent here is water, which we know has a boiling point of 100 degrees centigrade and a freezing point of 0 degrees centigrade. So for reference, I will just also write the molal boiling point and freezing point elevation constants. Molal boiling point elevation and freezing point depression constants of your solvent, which is water, which is this one here. Okay, so ang ginapangita is ang freezing point sang aton nga solution. So how do we solve that? Okay, so we need to we need a working equation wherein we can get the boiling point and the freezing point of the solution given with these values that we have. Okay, so let's go back to our working equation. So we know nga ang freezing point is equals to the freezing point of your water minus KFMI, right? And we know, so working equation man natin, ang boiling point of the solution is equals to boiling point of water plus KB na ni siya. KBMI, okay? Now, remember that these these values represent just one solution. So that means all of these will have the same value. So what remains constant in this case between these two equations is both the molality and the Vanatop factor, because these two equations represent for both the same aqueous solution with this boiling point. Okay? So since parehas lang ang solution ang gina-represent sa ining equation, we can actually manipulate these two equations here such that only Mi is on one side of the equation. Okay, so let's manipulate this one by one. So here, let's try making this a positive value by switching this, moving this to the left side, and the TF moving this to the right side. Okay, so you will have erase niya na. So final equation, so ang next mo expression is equals to KFMI is equals to TF of your water minus TF of your solution. Okay, then divide both sides of the equation with kf para ma-cancel out si kf sa left side. So what you get is this one, mi is equals to tf of water minus tf of your solution divided by kf. Okay, so on the other side, so here, this is pretty straightforward. Kaya i-transfer mo lang ni ang TBA, boiling points ng water ng expression sa this on the left side of the equation. So your KB MI is equals to TB minus, oops, sorry for the bad handwriting. Whoa. Minus the boiling point of your water. Okay. So, ang muna ang guaan. Okay? So, what's next is so, what's next here is that just like here, you divide this both sides of the equation by KB. So, para makancel si KB. So, ang final equation mo is MI is equals to TB minus TB of your water divided by KB. Okay? So, you substitute this equation on the left to this expression here to this equation on the right. So, ang matabo is, it would look like this. I'll just write it here so that I have more space for writing. So, freezing point, TF, ang muning mangin imo nga next equation divided by KF is equals to TB of your water minus TB lang gali, sorry, boiling point of your solution minus the boiling point of your pure water divided by KB. Okay, so multiply both sides with KF. So, buta ko siya. Hindi siya exponent, ha? Multiply both sides by KF para ma-cancel out si KF. So, what we'll have is this one minus TF is equals to KF minus KF rather multiplied by TB minus TB of your water. So I'll change this to a bracket since we already have a parentheses. To KB. Okay. Next is transpose this one to transpose TF to the transpose this one to the left, and this whole thing you move this to the right. Okay, therefore the freezing point of your solution is equals to the freezing point of the pure water minus this whole thing here. Okay, because positive ni siya, pag silo mo din mangin negative siya, so it will be KF divided by equal to TB minus TB of your pure water divided by KB. Okay. So then we substitute both sides of the equation. I'll just move this up here for a bit so that I have more space. So this will be now our working equation. Okay, so ang matabo, substitute nyo lang ang mga values nyo para makuha nyo ang freezing points ng inyong solution. So that is equals to 0 degrees centigrade, which is the freezing point of your water. I don't think it's enough. The space is enough. I'll move it up a notch again. So the freezing point of your water is equal to 0 degrees centigrade. Why is it not writing? There it goes. So minus 1.86, which is the mole freezing point depression constant. Oh, God. Or multiplied by the 100 minus 106.5 or rather 106.5 gali minus 106 ulit. Sorry about that. So 106.5 minus 100 divided by the boiling point elevation constant, which is 0.512. Okay, degrees centigrade per mole. Okay, this will cancel out. So you're plugging this in your scientific plugging this values in your scientific calculator. You will get the freezing point of the solution, which is negative 23.6 degrees centigrade. So this will be your final answer. So this is the end of my video. I hope you've learned something about it. I hope you understand the concepts and you understand how to approach problem-solving questions on boiling point elevation and freezing point depression of your solutions. And if you like this video, please hit the like button. And don't forget to subscribe to my YouTube channel for more chemistry related lectures. So again, this is the round bottom flask. See you guys